Notice the pattern. Name the rule. Explain why.
Welcome to the quail garden. In the morning light, you can see how everything here grows in neat, perfectly parallel rows of soil. This is Juniper. She's a California quail, leading her covey of downy chicks close together as they scurry across the earth to peck the ground. Watching over them is the wise math Shiva. He knows that when a garden is this orderly, the math starts to show itself. When Juniper's chicks settle into groups, they naturally form rows and columns. And when numbers organize like this, they create repeating patterns. Usually, we just memorize these patterns as rows of facts in a multiplication table, but we learn more about how numbers behave when we look past the list and study the formations themselves. Noticing a pattern helps us remember a result, but showing why it happens means we can predict how any group will behave. Here in the garden layout, Juniper lines up her chicks into 4 specific rows of 3. That gives us 12 chicks in total. We could guess, but how do we prove visually whether the number 12 is even or odd? If we take those 4 rows, we can physically divide them straight down the middle. The rows separate into 2 equal groups. By splitting the formation in half, each new brood now holds exactly 6 chicks. An even number is defined by its ability to split into 2 equal halves with nothing left over. Because 12 splits cleanly into 6 and 6, it must be even. This works for any set of 4 rows. Since 4 can always be divided into 2 equal pairs, any multiple of 4 will be an even number. Further down the path, these sequential garden beds are planted with exactly 5 seedlings each. As Juniper scurries past, she tracks the total number of shoots, accumulating 5, 10, 15, 20. Look at the leaf edge tags as the count climbs. The ones digit in that sequence cycles over and over. 5, 0, 5, 0. Here's the mechanic behind the pattern. Adding 1 bed lands you on a 5, but adding a second bed perfectly completes a unit of 10. Every third bed steps up to a 5 again, and every fourth bed locks into another full 10. The cycle repeats continuously. Because 2 5s will always create a perfect 10, a multiple of 5 will only ever end in a 0 or a 5. Now watch as a small brood of 3 chicks walks toward a brood of 5 chicks across the stone path. That gives us 8 chicks in total. If we ask them to pair off 2 by 2, will every single chick find a partner? This diagram breaks down what makes a number odd. An odd brood is just a set of pairs, plus exactly 1 leftover chick. When you add 2 odd groups together, those 2 leftover chicks step forward and form a new pair. Every odd brood brings 1 extra unit. When you add 2 odds together, those extras combine to make a pair, ensuring the final sum is perfectly even. Splitting rows in half, accumulating blocks of 10, and linking up leftover pairs. These are the living garden pictures that prove why the math behaves the way it does. Knowing the reason behind an operation gives you a predictable, logical system to rely on. The garden's tables are built on solid rules. So think about the number you get when you multiply 6 by 4. Based on what we saw with the rows, is that result even or odd? And how would Juniper show it with her chicks? A pattern with a proven mathematical reason is a promise you can always rely on.
Patterns keep promises. Rules make sense. Operations explain changes.